This video is on beta function as we continue to talk about special functions. Previously, we had considered introduction to special functions, and then afterwards we looked at gamma functions. As we're looking at gamma function, we discover that gamma function has a connection with beta function. So we are going to find that out in this video. So beta function is an important special function in mathematics with applications in calculus, probability, statistics, and physics. And it is defined by this: b of p comma q is equal to integral from 0 to 1 of x raised to power p minus 1. So the parameters are p and q here. So p minus 1, q minus 1. But with respect to x, that integral is with respect to x. So x raised to power p minus 1, then 1 minus x raised to power q minus 1. So I mean, it's giving a kind of sense about I think is it binomial theorem or something like that, where you have x into 1 minus x. So x raised to power something, 1 minus x raised to power something like that. So p and q are both positive, they are both greater than 0. So this function is also called the Euler beta integral. So for gamma 2, we had the Euler gamma integral, right? So this is the Euler beta integral. So we go straight to talk about the convergence of the beta integral. So if you consider beta of b of p comma q to be integral from 0 to 1 of x raised per p minus 1 minus x raised per q minus 1 dx, we examine convergence near the point x equals 0, when x is equal to 0 here. So it means this is gone. Okay, in fact, this whole thing just goes away. So the integrand behaves like this. You have x raised to p minus 1. So the integral then is like integral from 0, right, of x raised to power a dx. So, and this converges only if a is greater than minus 1. Thus, p minus 1 will have to be greater than minus 1. And that gives the fact that p is greater than 0, which is one of the conditions for the Euler beta integral in the first place. So we see that the integrand behaves like x raised to p minus 1. So what happens to p minus 1 affects the whole system. Now we have near that, so that's when we look at the convergence near x equals 0. What about near x equals 1? So it's more like equating this x to 0 and equating 1 minus x to 0. So that'll be where we have near x equals 1. So near x equals 1, the integrand behaves like this 1 minus x part now. So it behaves like 1 minus x raised to q minus 1. So the convergence requires that q should be greater than 0. So like that. So therefore, the beta integral converges when p is greater than 0 and q is also greater than 0. So we move on to the symmetry property. So the beta function satisfies that beta of p comma q is equal to beta of q comma p. So anyhow you go, you get the same result. So beta p comma q equals beta q comma p, basically. And how do we do that? We take the function. We start with beta of p comma q, which is integral from 0 to 1 of x raised to p minus q, 1 minus x raised to q minus 1 dx. So if we substitute 1 minus t for x, so if you substitute 1 minus t for x, so it means x here becomes 1 minus t. And then this 1 minus x then will just become, so if you want to get 1 minus x, right? So if you transfer x here, you have 1 minus x, and that will be equal to t. So 1 minus x becomes t. So x is now 1 minus t raised to p minus 1. 1 minus x is t raised to q minus 1. And then dx, of course, from here now, dx dt is minus 1. That means dx is minus dt. So now we have the integral set up differently with that substitution done. So what do we have? So we then have that we are differentiating with respect to t. So you have t raised to q minus 1, 1 minus t raised to p minus 1. So the way this is now, you see, we have, without doing so much, we have just substituting. So we now see that this same b of p comma q has become uh, the parameter has only changed, but then you have q minus 1, p minus 1, q minus 1 on top of t, just like you have p minus 1 on top of x here. Now you have q minus 1 on top of t, and p minus 1 on top of 1 minus t. So, you just have a reversal of p minus 1 and q minus 1. So that simply tells us that b of p comma q is the same thing as b of q minus q comma p. And that tells us simply that the beta function is symmetric. So b of p comma q is the same thing as b of q comma p. So look at this example. Okay, yeah, beta 1 1, of course, we can just to establish the fact, uh you want to evaluate beta b comma b of 1 comma 1 using the definition, right? So if you use the definition for 1 comma 1, so b is 1, q is 1, so that means you have 1 minus 1 0, 1 minus x raised by 1 minus 1, so x raised by 0, 1 minus x raised by 0, anything raised by 0 is 1, so you have 1 times 1 1. So at the end of the day, you just have integral of dx, and that is simply x. If you to evaluate that from 0 to 1, you get 1. So established, b beta of 1 comma 1 is simply 1. So with that in place, now we can project to other things. So you want to evaluate beta of 2 comma 3. So using the definition now, p minus 1, that'll be 2 minus 1, that's x raised power 1 there. The 1 minus x raised power q minus 1, that's 3 minus 1, that'll be 1 minus x raised power 2 dx. And we know that 1 minus x squared is the same thing as 1 minus 2x plus x squared, for polynomial expansion. We've done that quite a number of times. So x is 1 minus x squared, then is x minus 2x squared plus x cubed. So in essence, you have beta of 2 comma 3 to be integral from 0 to 1 of x minus 2x squared plus x cubed dx. So you now integrate that. So you have x squared over 2 minus 2x cubed over 3 plus x raised by 4 over 4 from 0 to 1. So if you do all the evaluation, you end up getting, to evaluate this now, you get at 1, that's 1 over 2. At 0, 0, so it's gone. So you have 1 over 2 minus, put 1, you have 2 over 3. 0, it's gone. So you have minus 2 over 3 plus, then put 1, that's 1 over 4. Add everything. So LCM is 12. 2 in 12 is 6, minus 3 in 12 is 4, 4 times 2, 8, plus 4 in 12 is 3, 3 times 1, 3. So 6 minus 8 minus 2 plus 3, that's 1 over 12. So beta 2 comma 3 is actually 1 over 12. So if you do that, simply means that beta 3 comma 2 is also 1 over 12 if you reverse it. Now we then have the Euler beta integral alternative form. So which alternative forms can we have for this? So using substitution, right? Using the substitution, x equals t over 1 plus t, the beta function then becomes beta of p comma q equals, so now the x you should have normally. So x here, this x now takes another form, which is t over 1 plus t. So okay, I think I should write that. I think I need to write that out. So look at the general form for the beta Euler integral, right? We have beta p comma q. So you have beta p comma q to be integral from 0 to 1 of x raised power p minus 1, 1 minus x raised power q minus 1 dx. And then if you now let x to be t over 1 plus t, I hope I got that correctly. Beta is t over 1 plus t. So if you make that substitution, that way, yeah, t over 1 plus t. So what happens here? So that means we have this now. Beta p comma q then becomes integral from 0 to 1. Okay, well, we have to substitute, we have to change everything. This is that 0 to 1 or 0 to infinity? Let me check again. I think it's 0 to infinity, not 0 to 1. So, well, by the time we translate, right, let's see, it's 0 to infinity. 0 to infinity. So let x be t all over 1 plus t. Before we change every other thing, right? So of course we now need dx. So dx dt is, this is more like t into 1 plus t raised by minus 1. So you can do product rule now. So dx dt is, so keep t and differentiate the other part. So bring my minus 1 down, differentiate inside, and you have 1 plus t. Reduce the power, that's 1 minus 2. Then all that added to differentiate t. All right, so that's 1. And then keep that intact, 1 plus t raised by minus 1. So that means that dx dt is equal to minus t all over 1 plus t raised by 2. And here you have plus 1 over 1 plus t, like that. So you can do dx dt to be equal to 1 plus t all squared. That'll be minus t plus 1 plus t, 1 plus t. That's 1 into 1 plus t. So we have dx dt to be equal to minus t plus 1 plus t all over 1 plus t all squared. So this cancels out, and we have dx dt to be equal to 1 all over 1 plus t all squared. So that means that dx itself is 1 all over 1 plus t all squared dt. So this replaces the x later on. Then apart from that, talking about the 0 to infinity, the limit, right? So we can say this, that at x equals 0, we have x to be t all over 1 plus t. That means we have, that implies that 0 is equal to t all over 1 plus t. So if we cross multiply, we have 0 into 1 plus t equals t. So this is 0 equals t. So that means the 0 is preserved. So t is 0 at that point. Then on the other hand, at t equals infinity, we have infinity equals t all over 1 plus t. So if you cross multiply, t is simply equal to infinity. So the limit doesn't change. It remains from 0 to infinity. So then we now come back to the original expression that beta of p comma q now is equal to integral 0 to infinity remains. Now we have said x should be t over 1 plus t. So you now have t over 1 plus t raised to power p minus 1. Then on the other hand, right, you have 1 minus x. So, okay, I think we have to deal with that. So you have uh, x is equal to t over 1 plus t. So that means that 1 minus x will have to be 1 minus t over 1 plus t. So that means LCM is 1 plus t. So this is 1 into 1 plus t minus t. So that will be 1 plus t minus t all over 1 plus t. So this cancels out. So you have 1 minus x to be 1 over 1 plus t. So now we have 1 over 1 plus t raised by q minus 1. And then for dx now, for dx, we have 1 over 1 plus t all squared dt. Okay? 1 over 1 plus t all squared dt. So then we have okay, let me see the form here. But by the time it's all done, right, we have t raised by p minus 1, 1 over t, 1 plus t raised by p plus q. So let's see how we arrive at that. Okay, so this is okay, let's just do it the way we can do it. I'm trying to see the best way to go. Okay, so you have integral from 0 to infinity. So this is t squared right here. So if we collect everything here, this is like t raised by p minus 1 up here, then 1 raised by q minus 1 up here, all over 1 plus t raised by p minus 1, then 1 plus t raised to power q minus 1 multiplied by 1 over 1 plus t raised to power 2 dt like this. So that we have integral from 0 to infinity as b of p comma q now. And that is, if you put all of this together, you can add the powers. So you have t raised by p minus 1. 1 raised by q minus 1 is simply 1. Then down here you have 1 plus t, all right, raised to power. So we can add all these three together. Raised to power p minus 1 plus q minus 1 plus 2. That's all the powers because everything is 1 plus t. All of this dt now. So beta of p comma q then becomes integral from 0 to infinity. So t raised to power p minus 1, then 1 plus t raised to power 2 cancels this like this. So we have p plus q, all of that dt. So in essence, we can say that this is another form for this transformation now. We have, so we can say therefore beta of p comma q is the same thing as integral from 0 to infinity t raised to power p minus 1 all over 1 plus t raised to power p plus q dt. So this is another form for this. When we do the transformation, x equals t all over 1 plus t like this. So that's exactly what we have here. So, and I have shown you the derivation. So that's how we get up to this point. So you can look through that again and see how that goes. So I'll just flash this because I've done it over on the worksheet already. So these are the things we need to just put them together and tidy up. Now, let's talk about gamma function. We're talking about beta function. Gamma function had been considered in the last video. So the gamma function is defined by gamma s, which is integral from 0 to infinity, e raised power minus x, then x raised power s minus 1 dx. If you also call it n, whatever. So gamma n is x raised power n minus 1, e raised power minus x dx, like that. So, and this happens for, it converges for s greater than 0. So it generalizes the factorial function since gamma n is n minus 1 factorial for positive integers n. So that's gamma function there. But we want to see how it is related to the beta function. So the beta gamma relation now. The beta and gamma function are related by beta of p comma q is equal to gamma p multiplied by gamma q over gamma p plus q. This is one of the most important identities in special functions. So we have been seeing a lot of special identities, like this is one of the most important ones we saw for beta and for gamma function. Yeah. So and the fact that gamma n plus 1 is the same thing as n gamma n, right? So things like this, we put them together and they make us very good with special functions. So proof of the beta gamma relation, for instance, if you start with gamma p gamma q, gamma p would have to be integral from 0 to infinity e raised power minus x raised power p minus 1 dx, while gamma q will be integral from 0 to infinity e raised power minus y raised power q minus 1 dy. So if you start with that, so you can put the integrals together. So you have integral from 0 to infinity, integral from 0 to infinity. Then for you have e raised power minus x, e raised power minus y, that's e raised power minus x plus y. On the other hand, you have x raised power p minus 1, you have y raised power q minus 1 dx dy. So if you substitute, for instance, if you say let x be ru, x is ru, and y is r into 1 minus u, for instance. So where now it means that um, where r is x plus y and u is x over x plus y, right? So you have x to be ru, and then y is equal to r into 1 minus u, and r itself is x plus y, and u is x over x plus y. So the Jacobian, if you get the Jacobian of that, right, dx dy will be r dr du, r dr du, and then if you substitute if you substitute whatever you have here, so you now have integral from 0 to infinity, then integral from 0 to 1 of e raised power minus r here, then x itself is ru raised power p minus 1, then you now have y is r into 1 minus u, so that's y r into 1 minus u raised power q minus 1, then dx is now r dr du, like this. And then from there you have then you try to tidy things up. So you have integral from 0 to infinity of e raised power minus this r alone, you have another r here. So you have r raised power p minus 1, you have another r raised power q minus 1 with this other r here. So by the time you add, so powers p minus 1 plus q minus 1 plus 1. So you end up getting r raised power p plus q minus 1 dr. And then on the other side, for the u's now, you have u raised power p minus 1, 1 minus u raised power q minus 1 du. So with this in place now, you then discover that this expression is as good as gamma p plus q, because gamma p plus q would have been e raised power minus something, something raised power p plus q minus 1. That's exactly what you have here. And on the other hand here, you have, this is the beta expression. Beta is from 0 to 1. So this is beta pq, which is u raised power p minus 1, 1 minus u raised power q minus 1 du. So starting with gamma p, gamma q, you end up with gamma p plus q, beta p comma q. So if you make beta p comma q the subject, you then have gamma q all over gamma p plus q, like that. So that's the connection we see between gamma function and beta function. So let's talk about beta function for integers. So using gamma n being equal to n minus 1 factorial, so we can obtain that beta mn is the same thing as n minus 1 factorial, n minus 1 factorial, because that'll be gamma n, gamma m, gamma n all over gamma m plus n, which is gamma m is n minus 1 factorial, gamma n is n minus 1 factorial, and gamma m plus n will be m plus n minus 1 factorial for positive integers m comma n. So using factorial now see, beta 3 comma 4 is simple using the factorial formula. Beta 3 comma 4 is simply gamma 3 gamma 4 all over gamma 7. So and gamma 3 is 2 that's 3 minus 1 2 factorial. Gamma 4 is 4 minus 1, which is 3 factorial. Gamma 7 is 7 minus 1, which is 6 factorial. So if you compute 2 factorial, which is 2, 3 factorial, which is 6, and 6 factorial, which is 720. So put everything together, you have beta 3 comma 4 to be 2 times 6 over 120, which is 1 over 60 overall. Then we also have the half integer values now. So an important gamma function value is the fact that gamma 1 over 2 is root pi. We established that in the last video on gamma function. So therefore, beta 1 over 2 comma 1 over 2 will have to be gamma half times gamma half all over gamma half plus half, which is gamma 1. So we know that gamma 1 is 1 already. Gamma half is square root of pi. So it means we have square root of pi times square root of pi, which is square root of pi square, which is simply pi, all over gamma 1, which is 1. So beta half comma half is simply pi right there. So you see gamma half is square root of pi. Beta half comma half is pi itself, because that's square root of pi multiplied by square root of pi divided by the gamma of 1, which is 1. Hence, we see that integral from 0 to 1 of dx all over square root of x into 1 minus x will simply give us pi. Because if you use, if you do half directly into the substitution, this is the kind of thing you end up getting, because you get, this is now pq, right? So since this is pq, if you have half minus 1, so that'll be x raised power minus half. That's why you have roots under here. And then, so 1 minus x raised power minus half again. So you have this coming down here, and this whole thing is equal to pi. So we then have the trigonometric form of the beta function. So using the substitution x equals sine squared theta. So if you use the substitution x equals sine squared theta, the beta function then becomes like this. You have beta pq. So I mean, if you substitute sine squared theta for, beta function is already x raised power p minus 1. Okay, maybe I should write here. Okay, and we are substituting x equals sine squared theta. So it's more about substitutions. So just like what we substituted x equals t over 1 plus t here to get this now. So we can also substitute, having beta p comma q to be integral from 0 to 1. Hope that's correct. Integral from 0 to infinity. Now I think we need to establish something. Is it 0 to 1 or 0 to infinity? It keeps changing forms. Let's see. Beta is 0 to infinity. But yeah, it's always 0 to infinity. So where is this 0 to 1 coming from? Is it another form now? Okay, let's do our 0 to infinity and see what happens. So beta pq is 0 to infinity, and then we have x raised by p minus 1, q raised by x, 1 minus x raised by q minus 1 dx. So if you let x be sine squared theta, so uh, we're then saying that beta p comma q will have to be integral from 0 to infinity, 0 to infinity, then x, that's sine squared theta, all over p minus 1. And then we have 1 minus sine squared theta raised by q minus 1. And then, of course, we have dx. So dx here will have to be, dx d theta is actually, the x d theta here is equal to, if you differentiate this now, bring down the power 2, differentiate sine, you get cos theta, and then you have sine theta. So overall, dx is 2 sine theta cos theta d theta, all of that. Okay, let me write that out better. So we say that this one is the same thing as dx equals 2 sine theta cos theta d theta, like this. So at the end of the day, this is 2 sine theta cos theta d theta. Finally, so we then have beta p comma q to be integral from 0 to infinity. Then we have uh sine 2p minus 1 theta. That's the power now. Then here, this is cos. So 1 minus sine squared theta is cos squared theta. So that's cos 2 into q minus 1. Then we have 2 sine theta cos theta d theta. So we can do some tidying up here. So 2 comes out here. So we have 2 from 0 to infinity. Then sine 2p minus 1. That's sine 2p. That's sine 2p minus 2. So but you have one of this here. So that'll be sine 2p. Instead of 2p minus 2, that'll be 2p minus 2 plus 1. So that'll be 2p minus 1 theta cos 2q minus 1 theta, because this is 2q minus 2 plus 1 that comes from this cos theta. So that's cos 2q minus 1, and everything is d theta here. So that's the form we have in trig. In terms of trig, that's why we have this now. So of course, so sine 2p minus 1 is like sine theta raised by 2p minus 1. So that's exactly what we have here. But one thing I've not done is the transformation for 0 to infinity. So for 0 to infinity now, okay, before I even come to this place, I should have done all of that, right? So we have so 0 equals sine squared theta. So if you take square root of both sides, so 0 is equal to sine theta. So that implies that theta is arcsine of 0. Arcsine of 0 is simply 0. So this 0 remains. Then for infinity, so you have infinity sine squared theta, sine squared theta. So if you square both sides, that's infinity equals sine theta. I think this is where the whole, sine 90 degrees is 1. So I think we need to be very sure of the, yeah, okay, beta function generally is 0 to 1. I wonder, why did we not have 0 to infinity in other situations? I think that's where the challenge is coming from. Why we having 0 to infinity elsewhere? Okay, no. The original thing is 0 to 1. And it becomes 0 to infinity here. Okay, gamma is 0 to infinity. I guess that's what one of the issues. Okay, so it's actually 0 to 1. So if it's 0 to 1, then this actually works. So we know that if it is 0 to 1, if you square both sides, this is 1 sine theta. So theta is arcsine of 1. And sine 90 gives us 1. That's pi over 2. And that is why when we come here, we can then have pi over 2. This is pi over 2. And this is also pi over 2. So I might have, anyway, I've written 0 to infinity for sigma. I mean, for beta, that's not okay. But I think I need to verify. So this is okay, right? So I think what I need to verify here is this. So if we start with this, this starts with 0 to 1, right? So this one here should be 0 to 1. So to take care of that, let's see what happens here. Um, at 0, right? At t equals 1, actually. So this is 1 here. So we have t equals 1 plus t, right? Then if we try to tidy this up, this implies that we have t minus t equals 1. So that's 0 equals 1. It doesn't make sense. And that is why here t becomes undefined. It's not defined. That's why we have 0 to infinity here. So the original thing is 0 to 1. So but if we do this transformation, x equals t all over 1 plus t, then it becomes infinity in that regard. So I think that's the issue that should be addressed in that case. So yeah, with all of that in place, then let's talk about beta function. Okay, we've done all of this. So half integer taken care of. Then trig form of beta function already done. Trigonometric integral formula then becomes this now. That, based on this idea now, so from the beta function, we can then say that the integral from 0 to pi over 2 of sine mx cos n x dx can be expressed as this. Divide both sides by 2. So this is like half beta pq. Okay? So half beta pq. So now, if we say 2p minus 1 is equal to m, so at the end of the day, we have this kind of transformations here. Okay, I guess I want to still do that. So if this is m and this is n, let's see what happens. So we have So if we let 2p minus 1 be equal to m, okay? So, we have p here, we have q here. So we need to find p and q. So 2p minus 1 equals m. That means 2p is equal to m plus 1. If you transfer this, then p is m plus 1 all over 2, settled. On the other hand, we have 2q minus 1 equals n. So that means 2q is equal to n plus 1. So that means q is n plus 1 all over 2. So in essence now, we can then have so we can have beta pq now becomes beta m plus 1 over 2 n plus 1 over 2. And then on the other side we have the integral. So this is integral of, that'll be 2 integral, or let's say beta pq implies this, right? So it implies this. So that'll be 2 from 0 to infinity. Is it infinity now? Pi over 2, that's 90. So 0 to pi over 2, okay, will now be, so this is m, this is n. So we have sine m theta cos n theta d theta. So this now becomes a standard formula that we can use. So we can divide both sides by 2. So this 2 goes to divide this. So we can say, therefore, integral from 0 to pi over 2 sine m theta cos n theta d theta is equal to 2 beta m plus 1 over 2 n plus 1 over 2. So this now becomes a standard formula we can always use. So if you have an integral looking like this from 0 to pi over 2, you can just, instead of stressing yourself out trying to multiply, you can just write out the beta function and you're good to go. So we'll see some examples of that, I believe. So let's look at some trigonometric example. So here you have integral from 0 to pi over 2 of sine cube x dx. So definitely this, so here now, sine, the m here is 3 and n here is 0 because cos does not exist. So in that case now you just have half beta of m is now 3 plus 1 all over 2. That's 4 over 2, which is 2. Then on the other hand, for cos does not exist, so it's the n there is 0. So 0 plus 1 over 2, that's half. That's why we have half beta 2 comma half. So we can then use the what we know. So now use the beta gamma relation. So you already have half here, and this is gamma 2 gamma half all over gamma 5 over 2. So we know that gamma 2 is 1 because that'll be 2 minus 1 factorial, which is 1 factorial, and that is 1. Then gamma half is root pi, taken care of. Gamma 5 over 2 is what we now need to talk about. Of course, we know that gamma 5 over 2 is okay, gamma 5 over 2, from what we know from gamma that we dealt with. So gamma 5 over 2 is the same thing as 3 over 2 gamma 3 over 2. And that is the same thing as 3 over 2 times gamma 3 over 2 is now half gamma half. And that will be 3 over 2 times 1 over 2. Gamma half is square root of pi. So beware of gamma and square root. They are different. They are not the same. So this now is 3 over 4 root pi. So if you bring that up here, then you have it's 3 over 4 root pi. So if you fix everything together, so you have 1 over 2 plus 1 over 3 over 4. Okay, I think we already have root pi up there already. So we have root pi. So the root pi, we cancel the root pi here. So you have, tidy all of that up, you have 2 over 3. So instead of stressing yourself out trying to differentiate this endlessly, you just know that this is 2 over 3 straight up from beta and gamma connections. So let's talk about some applications in probability of these things. So the beta function appears naturally in probability theory. So the beta distribution is defined by f of x equals 1 over beta of alpha comma beta x raised by alpha minus 1 minus x raised by beta minus 1. So this is what the beta distribution looks like. And this happens for x lying between 0 and 1, where alpha and beta must be greater than 0, just like the p and q we have in the original Euler beta integral. So the beta function acts as the normalization constant, ensuring the integral from 0 to 1 of f of x dx is equal to 1. Of course, that's one thing we need to know. That is one thing that makes a probability distribution actually correct, that integral from 0 to 1 is always 1, or integral over the whole hog is 1. Then we have mean and variance of beta distribution. So if x is distributed according to beta with parameters alpha and beta. Then mean is the expectation of x is alpha over alpha plus beta. That's the mean. And the variance of x is alpha beta over alpha plus beta all squared into alpha plus beta plus 1. So then we have the probability example. So for the probability example, suppose x is beta distributed with parameters 2, 3. Then we have f of x equals 1 over beta 2, 3 x into 1 minus x all squared. So since we already know that beta 2, 3, we can easily find this. That's 1 over 12. And then we can get that f of x is half x. So f of x now is uh 12x. Oh yeah, because this is 1 over beta 2, 3. That's 1 over 1 over 12, which is 12. So that's 12x is 1 minus x squared. So if you then need to find probability that x is less than half, so we have probability x less than half to be integral from 0 to half of that probability distribution or probability function. That's 12x into 1 minus x all squared dx. Then we expand all that. The rest is just a calculus. You can bring out 12, expand this 1 minus x squared multiplied by x gives us x minus 2x squared plus x cubed dx. So integrate all that and tidy things up. So you have x squared over 2 minus 2x cubed over 3 plus x raised to power 4 over 4 from 0 to half. So put half. Of course, all the zeros will be gone. So put half. So you have half squared, that's 1 over 4. So 1 over 4, 4 goes down, that's 1 over 8. Then 1 over 2 raised to power 3, that's 1 over 8. So 2 times 1 over 8 is 1 over 4. So the 4 goes down, that's 12. That's why you have 1 over 12 here. Then 1 over 2 raised to power 4, that's 1 over 16, I believe. So 16 times 4 comes down, that's 1 over 64. So you can then take the LCM, which is 192, and then you have 8 in 192 is 24, 12 in 192 is 16, 64 in 192 is 3. So you have 12 times 11 over 192. So 12 goes in 192, you have 16. So that's 11 over 16 overall. So therefore, probability that x is less than half for that function is 11 over 16. Then we have integral identities. So that identity one is that integral from 0 to 1 of x raised power m into 1 minus x raised power n dx is simply m factorial n factorial all over m plus n plus 1 factorial. All right. So for integers m and n greater than or equal to 0, like that. All right. So that's more like gamma m plus n, gamma m plus 1, gamma n plus 1 all over gamma m plus n plus 2, like that. So then another identity is this, that identity 2, integral from 0 to infinity of x raised power a minus 1 over 1 plus x dx is pi cosec pi a with a lying between 0 and 1. And identity 3 is integral from 0 to pi over 2 sine mx dx is gamma pi, square root of pi gamma m plus 1 over 2, 2 gamma m plus m over 2 plus 1. That's another identity. So they may be useful in some regard. So reduction formula then. So the beta function satisfies the recurrence relation that beta of p comma q plus 1 is the same thing as this q all over p plus q, then beta pq. Similarly, beta of p plus 1 comma q can then be p over p plus q. Whatever adds 1 goes up and is divided by its addition to the other parameter multiplied by beta of pq. So we can have Python codes now. So computing beta functions. So just import beta from scipy.special. Under scientific computing with Python, I worked with this scipy special a lot. I had I have a whole video on that. In fact, that was what inspired this video. So beta 2 comma 3, it's 1 over 12, and 1 over 12, I'm sure if you print 1 over 12, that's exactly what you get. Print 1 divided by 12 also. So you get exactly, so you see this is 1 over 12 here. Then beta 0 0.5, 0 0.5, you get 3 point, that's pi, right? 3.142, because that's root pi times root pi over 1. Then coming here, numerical integration verification. So from scipy.integrate, you want to import quad. So I also did this under scientific computation with Python. So if you define the function x into 1 minus x all squared, and you integrate it over 0 to 1, so just to compare how the beta thing goes, so you then have 0 0.0833, and that's exactly what we have coming on here. Then we have plotting beta distributions. So here now we have pairs of beta distributions, right? You have 1 1 2 5 5 2 2 2. So we want to plot all of this, and in that case you need to import beta from scipy.stats, and then you have NumPy and Matplotlib for the usual duties they do. So 1 1 is the blue line, straight line. So of course we know that's 1. Then we have 2 5. 2 5 is the orange line, and then 5 2 is the blue line, and then you have 2 2. 2 2 is this one that looks like a parabola, that should we say it is concave downwards. I hope that's the best way to say it. So you have 1 1 2 5 5 2 2 5. So you see 5 2 and 2 5, they are kind of, should I say, symmetric now? You know, so you see 2 5 and then 5 2. That goes like that. So in summary, by definition, we say that the beta function is beta of p comma q equals integral from 0 to 1 x raised per p minus 1 minus x raised per q minus 1 dx. And it is symmetrical, meaning that beta of p comma q is equal to beta of q minus q comma p. Then it's a beta gamma relation, which means that beta of p comma q is the same thing as gamma p gamma q all over gamma p plus q. And then we have the integer formula for beta. So integer formula for integers now, beta m comma n can now be, of course, gamma. This should be gamma m, gamma p, gamma n. So gamma m is m minus 1 factorial, gamma n is n minus 1 factorial. Gamma m plus n, that's m plus n minus 1. So if it was for p and q also, right? But because this is general and this is for integer, that's why we just change the parameters. So in trigonometric form, we can also have beta of p comma q to be 2 integral from 0 to pi over 2 sine 2p minus 1 theta cos 2q minus 1 theta d theta. And we have the beta distribution to be f of x equals, that's not in probability, f of x equals 1 over beta alpha comma beta x raised by alpha minus 1 minus x raised by beta minus 1. So then we have practice problems as usual. So we have our practice problems to take care of. So let me do my usual delineation. Not necessary, but I just like to do it. Just to divide into groups. And of course, as usual, I'm going to solve 2 of this. Okay, still up there. Um, okay. Yeah, so we have all of that. So a line at 10 and then a line at 20. So let me flash the problems. So you have 1 to 5 right here. Then you have 6 to 10 here. And then you have 11 to 15. And then 16 to 20. So I'll be taking 2 of this as I'll be solving them on the worksheet. I'll be solving problem 8 and problem 9. So let's go and see what that looks like. So okay, let me show problem 8 again. Problem 8 says to evaluate integral from 0 to infinity of x squared over 1 plus x raised by 5 dx. And 9 says to evaluate integral from 0 to pi over 2 of sine 4x cos squared x dx. So we'll apply some of the relationships we were able to develop while dealing with all of those things. So let's go for this now. So problem 8. Problem 8. So we want to evaluate integral from 0 to infinity x squared all over 1 plus x raised to power 5 dx. Okay, so this is looking like when you have substituted x to be t over 1 plus t. So so that's, you have to call that using, so because that you need to know what any problem you have, you need to know what it looks like using the beta function identity. Using the beta function identity, where that comes from is beta p comma q equals integral from 0 to infinity for t raised to power p minus 1 all over 1 plus t raised to power p plus q dt. Now, how do you know this is what it looks like? Number one, this is from the Euler beta integral is from 0 to 1, and this is from 0 to infinity. The only case we have 0 to infinity is when that case where you have said x is equal to t all over 1 plus t. So that should remind you that if you have 0 to pi over 2, you're dealing with a trig case. So now this has got to relate with this now, because this is the only case where we have 0 to infinity. So with that in place now, then we need to identify the terms. Of course, so clearly here you can say x is equal to t. So we have to identify the part So we then identify, we identify. So if you look at what this is now, so if x is equal to t, so the x is the t, so it means that if this is x is this, so it means p minus 1 now, this p minus 1 will have to be equal to 2, okay? P minus 1 is equal to 2. So identify that p minus 1 is equal to 2. That implies that p is equal to 2 plus 1, and that means that p is equal to 3. We identify that and keep that. And another thing we identify is we also see that this is 1 plus t. Already t and x are the same. So that means that p plus q should be 5. Okay? So we have to identify that p plus q is equal to 5. And we already have p. So that implies that p, that's 3 plus q, is equal to 5. And that means q is equal to 5 minus 3, which tells us that q is simply equal to 2. So if that is the case, once we have got p and q, then the rest is story. Then the rest is simply story. So we can then say, so now, integral from 0 to infinity of x squared all over 1 plus x raised to power 5 dx will have to be beta 3 comma 2. And I mean, this is now easy peasy because we know beta 3 comma 2 is gamma 3 gamma 2 all over gamma 3 plus 2, like that. So that means that that is gamma 3 gamma 2, okay, not square root, gamma all over gamma 5. So that means we know gamma 3 is 3 minus 1 factorial, gamma 2 is 2 minus 1 factorial, gamma 5 is 5 minus 1 factorial. So that means we have 2 factorial, 1 factorial, all over 4 factorial. So that means we have 2 factorial up here. 1 factorial is 1. 4 factorial is 4 times 3 times 2 factorial. This cancels out. So I stop at 2 factorial because we know we can stop there. So that's now 1 over 12 easily. So 1 over 12. So with that, now we can say, therefore, integral from 0 to infinity of x raised to power 2 all over 1 plus x raised to power 5 dx is simply beta 3 comma 2, which is 1 over 12. And that's it. Okay, using that identity. That's problem 8. Then we go for problem 9. So problem 9. So for problem 9 now, we need to evaluate. We need to evaluate integral from 0 to pi over 2. Now, once you see, if you see 0 to 1, you use the original Euler Beta Integral. If you see 0 to infinity, you use the identity where you have transformed x using x equals t over 1 plus t. Then if you see 0 to pi over 2, of course, simply talking about trig. So this is sine 4x cos 2x dx. So, of course, this is the case of the integral. So in this case, we use the trigonometric, beta function formula, So it's more about comparisons now. So it has integral from 0 to pi over 2 of sine mx cos nx dx, which is equal to half beta into n plus 1 over 2, n plus 1 over 2. So all we need to do now is to identify our m and n. That's all. So by doing that, right, we identify, so we identify, we identify So here, this one is the comparison is even more direct. So 0 to pi over 2, 0 to pi over 2. Then we can then dx is dx even. So it means that the power of sine is m, and that the power of sine here is 4. So we identify that m is equal to 4. What else do we identify? That the power of cos is n here, and the power of cos here is 2. That means m is 4 and n is 2. And once that is settled, then we can just say, therefore, integral from 0 to pi over 2 of sine 4x cos 2x dx is simply 1 over 2 beta n plus 1, that's 4 plus 1, all over 2, then n plus 1, that's 2 plus 1, all over 2, like that. So we then have half beta 5 over 2, 3 over 2, like that. So if we then use the beta gamma relation, using the beta gamma relation, using the beta gamma relation, using the beta gamma relation, we then have that half beta 5 over 2, 3 over 2 will simply be 1 over 2 times gamma 5 over 2 gamma 3 over 2 all over gamma 5 over 2 plus 3 over 2. So that means we have half times gamma 5 over 2. Okay, so we go step by step, right? So gamma 5 over 2. Let me see what we can do here. I want to see the best way to go. Okay, so we have, okay, let's do it this way. We know gamma 5 over 2. I can do it in a smart way. Gamma 5 over 2 is 3 over 2 gamma 3 over 2 times gamma 3 over 2. Okay, I mean the whole of gamma 3. So that's gamma 3 over 2 all over 5 over 2 plus 5 over 2 plus 3 over 2, that's 8 over 2, that's gamma 4 right here. So that one can be easily taken care of. But see, this is half times 3, so we can even bring 3 over 2 out. Then gamma 3 over 2, now we have gamma 3 over 2 squared, okay? So that we don't have to do double work. So we can square that already. And gamma 4 is 4 minus 1 factorial as we know it already. So let's go gradually now. So we have 1 over 2 times 3 over 2. So gamma 3 over 2 is like, is not like 1 over 2 gamma 1 over 2 all raised to power 2 now. Then 4 factorial is 3. 4 minus 1 factorial is 3 factorial, right? So here now we have 1 over 2 dot 3 over 2, then 1 over 2. So we have 1 over 2 there. Then gamma half is square root of pi. You know, gamma half is square root of pi. All of this squared, right? So if I had not squared it, I would have done them separately. And that doesn't, I mean, this is a smarter way. So we know gamma half is square root of pi. And 3 factorial is simply 3 times 2 times 1. That is 6, right? So we then have 1 over 2 times 3 over 2. Then 1 over 2 squared is 1 over 4. Pi squared, pi squared is root pi squared is simply pi. Then 3 times 2 times 1 is 6. So we are almost there now. So this is 3 here, this is 2 down here. So we just have pi all over 2 times 2, 4, 4 times 4, 16. 16 times 2, that's 32. And that's what we get, pi over 32. So we can conclude that, so integral from 0 to pi over 2 sine 4x cos squared x dx. If you deal with it like a not proper trig, it's going to be more tedious because you have to integrate first. You may have to use some trigonometric identity, then you substitute from 0 to pi over 2, and you still end up getting pi over 32. But with beta function and gamma, you have got your pi over 32 still. So with that, we come to the end of this interesting video on beta function. It's pretty lengthy, but it's worth it. So you want to go step by step. Once again, I flashed the practice problems 1 to 5, 6 to 10, 11 to 15, and then 16 to 20. So with all of this in place, we are done with this video on beta function. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, the question is, what exactly are you waiting for? Why not go ahead and subscribe now? Hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges, some perks, which you'll find out as you click. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.